Good morning and welcome you all to the NPTEL course Advanced Distribution System Analysis and Operation, and we are moving with our module 2 DER Integrated Distribution Network Modeling. And in the last few classes we have seen the power flow model of the distribution network feeder or the lines. We have derived the bus injection model and its linear form. We have derived the branch flow model, original 3-phase branch flow model, its signal phase equivalent model, and the relaxations from its original model. But we have seen that the busing branch flow model for 3-phase system is not exact, that is there because of the mutual coupling. So, the solution from it, if you want good solution from us for a single 3-phase system and a fast solution, because if you are solving a non-convex problem or a non-linear problem, it will take huge time to solve, and that will enhance or that will amplify with the size of the network. So, the easiest way that you linearize it and then solve it. Linear solution is always very fast. So, in this lecture we will see how you can linearize the branch flow model for a 3-phase unbalanced distribution network. So, we will start with the 3-phase original nonlinear power flow model that we know. This is your power balance equation, this is your voltage equation, and you have a relationship equation between voltage, current and power. So, these two equation we have already told, they are linear for variable L and V, right, L and V. Okay. If you replace this V with the V square, then it is no more linear. Okay. So, keep in mind we have to solve keeping V small Vm as the variable, not capital Vm square. Okay. So, it is linear for V and L, but the relationship between power flow voltage and the L small l, that is quadratic equality. So, these three are inequality. Now, how to get rid of these three? So, for perfect linearization, the term LNM, that means this term, if you can go out of it, why you need these three equations? Because this LNM is present here, LNM is present here. So, to establish what is LNM, you have to take these three equations, right. So, if you can get rid of this disturbing element from your equation, then you are good. So, for doing that, if you can remove this, then your power flow model will become completely linear. Again, your SNM is a full matrix, we have seen already. AB and henceforth it is a full matrix, right. So, for power balance equation appear for mutual power flow as well. That means, you have to put mutual power flow balance equation as well. Those are redundant values. You do not need those equations actually, because mutual power flow balance is not required. So, simplification must be adopted that this matrix will become diagonal, that we have done in the non-linear case as well. That is simplification, that you will only get the diagonal element for the power balance. So, for doing that we will take two assumptions. First assumption, that line losses are very small compared to the actual amount of power flow in the line. That is true actually. If your line is carrying, let us say 10 megawatt, then your line loss is supposed to be, most of the cases it is around 10% of that power. Okay. That means, it has to be 1 megawatt. If it is a very bad system, then it is 10%. If it is a good system, that will be lower than that, it may be 5% or 2%. Okay. So, the loss of the system is comparatively very less, and that is also a desirable condition, because if you are sending a certain amount of power from one end to another end and you are losing a huge amount of power in the path, then that path is not good. So, the first considerations we will take that the loss in the network is compared with the power flow, it is very less. Okay. And the second, that the voltages are nearly balanced, what we took in the last time as well, that your angles are exactly 120 degree apart from each other. If this is your VA, this is your VV, this is your VC, they are exactly 120 degree apart, and the magnitude of VA and magnitude of VV is also comparable. They are close, they are in proximity, not very much they are deviating from themselves. If these two assumptions A1 and A2, if we hold it, then with assumption A1, this term will become very less. This is your loss term, I square z. If this term is neglected, then this will become 0. These two terms will become 0. So, we have wrote it like this. You have SNM plus your net power, that means if this is your bus number n, this is your bus number m, this is your SM net, and then you have output power till W. Okay. So, this is your SNM and this is your SMW. Okay. So, how much power you are getting? Plus equal to your net power demand at that node and how much you are sending to your next bus. Then your voltage equation is also there with this, without this ZNM and LNM component. So, this has become now your reduced version of your branch flow model. So, here you do not have this LNM term, this term is not there. If this term is not there, then you do not need also these three equations, because ultimately we have to, for the physics, we have to keep the power balance maintained and the voltage equations maintained. Now, to keep these two things, we kept the square of the current terms, and for that we introduced these three equations, where the current is related with the power and the voltage. But now, in the linear formulation or this modified formulation, we do not have that square current term. So, if you do not have that, so that means you need not this three equations of quadratic equalities. Now, with assumption A2, the system will become nearly balanced. That means, the off diagonal elements of SNM will become negligible compared to the diagonal elements. Okay? So, that means your power balance equation is present only for the diagonal elements. So, your new or revised branch flow model will look like diagonal of SNM equals to your actual demand at that phase, then plus diagonal element of that. That means, you can write it as a phase net plus your S and W A. Similarly, you can write it for BB, you can write it for CC. Okay. This is your diagonal element, and voltage also you can write like this. Now, you split up this one, this is your apparent power, you can split it into two part, that is the real and the imaginary part. So, if you split it, then you will get your active and reactive power balance equation at each and every bus and phase. Those are decoupled from each other. You are not getting any mutually coupled term in these two equations. Okay. Again, for the voltage equation, you have ZNM and SNM star and ZNM star and SNM. Now, this term if you see at the LHS, what is that? that is actually Vm multiplied with Vm star. Okay. So, if you multiply complex number with its complex conjugate, then what you will get? Only the magnitude is square, the square of the magnitude. That means it is a real number. It has nothing to do with the imaginary part. So, in the right hand side, if you expand this right hand side, then the imaginary part of that right hand side is 0. Only the real part is present. So, this equation you can revised and write like Vmh for a per phase basis equals to Vnh minus real part of this and real part of this is equal. Only the imaginary part has plus and minus opposite sign, but the real part is same. So, you can write that it is 2 of real part of any either of the term. Okay? Understood how we wrote it? But in this equation you have your mutual coupling, but that is only for this z term. So, you have not completely negated or you have not completely omitted the mutual coupling term, you have considered it, but only for determining the voltage, not with the power flow. So, this is your complete linear distribution flow model, which is named as Lin-Dist flow model, where you have an active power balance equation, you have a reactive power balance equation and a voltage equation, square of the voltage equation. Okay, got it? So, this is your linear BFM, and this is highly used when you want your 3-phase system to be solved quickly, or let us say real time, if you want real time solution. So, for at that time we always use this linear BFM to solve. Now, we will quantify how the unbalancing effect in the distribution network. Okay. First, we will see what are the reasons for unbalancing in distribution network. First is that single phase and unevenly distributed loads. That is obvious, like let us say it is a 3-phase system, it may possible that one phase has a load of SL1 or let us say that is 10 kilowatt, second phase has a load of 20 kilowatt and third phase has a load of 30 kilowatt. 3 homes are connected. All homes must not have the same amount of power requirement. So, one is 10 kilowatt, one is 20, one is 30. If it is so, then though it is a 3-phase connection, but all the 3 phases are experiencing different amount of load. So, you will get unevenly distributed load, and sometime it is happened that you have a 3-phase system, after a certain time you have 2 phase only going move forward and one phase is ending here, and again after one phase is going and one phase is ending here. So, you have here only 2 phases, here only single one phase. So, if that is the case, then at this bus it is unbalanced, at this bus it is also unbalanced. So, unevenly distributed loads and single phase loads cause your unbalancing in the network. Second reason is the unequal distributed energy resources integration, because we are integrating DERs, rooftop DERs at the home level. That means, we are connecting it to the single phase level. So, the connection or the amount of solar panels we are connecting, that is not equal at all the phases, because each home is not installing the same capacity of the solar panel. One is let us say installing 5 kilowatt, one is let us say 2 kilowatt, one is let us say doing, he is a very rich and he is doing 10 kilowatt. So, your DER's penetration is not even equal at all the phases. That means, your load is also not equal, your source is also not equal. So, obviously, your network, if you have a 3-phase connection as well, still you will experience an unbalancing effect. Then you have a phase specific switching operation. That means, if you have a capacitor bank connected at each and every phase, and let us say only one phase is experiencing lack of reactive power, then you will turn on only the capacitor for it. So, intentionally you are giving more reactive power to a network. So, that will also cause unbalancing. Then one phase is experiencing more load growth, that is also possible, that you are connecting a customer to only one phase. So, then it will be an uneven distributed distribution of the customers among the phases, and then single phase network beyond the distribution transformer. That means, after the transformer, what I told, you have only two phases coming out or single phases coming out. So, if these are the cases, then your system will experience unbalancing effect in the network. So, what are the consequences for it? First thing is that overheating of the equipment. Whatever is the balance or three phase motors or three phase devices you have, they will get unbalanced current obviously. If they are getting unbalanced current, then there will be heating in that three phase devices, and if the heating is there, then obviously their efficiency will drop down. The system loss will increase. Why the system loss will increase? Because you have three phases. Previously you have a neutral also here, let us say this is A, B, C and this is neutral. So, if it is a balance, then I A, I B and I C, the summation of this will be equals to 0. That means your neutral current I N equals to 0 previously. But now, if you have an unbalancing effect, then this is not equals to 0. Then you have a current flow flowing through the neutral conductor as well. So, you have a current flow through an wire, then your neutral conductor will also cause some, also give some network loss. So, your system loss will increase. Then the same thing, your neutral conductor will become overloaded, because generally we design the neutral conductor in such a way, or the amount of conducting material or volume of the material we used in the neutral, that is mostly half of the volume we used for the phases. And we generally think that a system will run in the balance condition and very minimal amount of current will flow through the neutral. Now, if due to your unbalancing effect, if that amplifies in such a manner that your neutral current will become very high, so at that time your neutral conductor will become overloaded. Then if you connect a three phase DER, let us say wind turbine, that is a three phase connection, DFIG is a three phase generator. If you connect it, but in your grid everything is unbalanced, so obviously it will also draw an unbalanced current. So, it will, the system will become unbalanced. If that is there, then your DER performance will also degrade, because it is supposed to give you balanced system. Then you will get voltage fluctuation and flickers in the different phases, like one phase is experiencing very high voltage, another experiencing very low voltage, then you will get a voltage fluctuation between the phases. So, how to measure this voltage unbalance effects? So, there are mainly two indices which is widely adopted worldwide to measure this voltage unbalancing effect. One is called phase voltage unbalance rate or PVUR. Okay. What is this PVUR? PVUR says that first you calculate the average of the three phase voltage magnitudes. Okay. Take the average and see the maximum deviation of the phase voltages from that average value. Maximum deviation of the phase voltages from the average value. That means, for a particular phase VA, your PVUR value will be divided by V average into 100%. Okay. So, this is how your PVUR values are calculated, and National Electrical Manufacturers Association says that this value must not go more than 1%. They are very strict about their unbalancing thing. They says that any equipment you design or any system it is running, that unbalancing must not be more than 1%. NC or the American National Standards Institute, they are little bit relaxed from NEMA, and they says in the standard C84.1 that this PVUR value is maximum allowable limit is 3%. So, NEMA says it is 1%, but for NC this is 3%. Another index says that is the voltage unbalance factor, which takes the magnitude of the negative sequence voltage by magnitude of the positive sequence voltage. Now, why the negative sequence voltage? You will only get negative sequence voltage when your system is running under unbalanced condition. For balanced system, you will never get negative sequence component. It is always positive sequence. Now, you may ask, why not then zero sequence? That is also you will see from the unbalancing effect only. But zero sequence component will only arise when the grounding is affected, because zero sequence current or zero sequence voltage drop you will get in the ground path. So, if let us say a fault occurs, let us say there is an LL fault, ground is not involved. If ground is not involved, then at zero sequence you will not get anything. So, if you do it only with the zero sequence by positive sequence, then you will say no, my VUF is very good, that is 0%, because your zero sequence portion is 0. But that is not the case, you got an unbalance in your system. So, that is why we take the negative sequence, because any kind of unbalancing, any kind of faulted or unbalancing effect always give you the negative sequence, and positive sequence is always present, that is present in balanced condition, that is present in unbalanced condition. On top of it, if you have negative sequence component, then we will say that system is incurring an unbalanced operation. So, with this, if you have the IEEE standard 1159 and IEC standard 61000313, they told that the VUF or voltage unbalancing factor, that values as per IEEE is should be around 2% or lesser than 2%, the maximum value is 2%, and as per IEC the upper limit is 3%. So, if you take this PVUR or voltage unbalancing effect, unbalance factor, we can see the maximum allowable unbalancing effect in a network is maximum to be a 3%, not more than that. So, whatever conditions or you can say the approximations we took before, that will say that the voltage of them is close in proximity and it is close to one angle 120 degree, only the phase difference is there and that is also 120 degree. That is quite true, because if it is only 3% deviation, 3% is the maximum deviation. So, it is around 1% or 2%. If we go with the ANSI NEMA, then it will be lesser than 1%. So, then you can tell that though we have an unbalanced system, but still it is running in the proximity of the balanced system. With this, we will end this module 2, and here we have learned the modeling of all the DERs, loads and the networks, both the current model and the power model. Now, in the subsequent modules, we will use this model to solve different distribution network analysis problems. Okay? Thank you.